Good morning, good afternoon, good evening, and welcome back to the XDI Experience live show. Each week, I talk about what's driving demand in the fourth industrial revolution. Each week, I talk about the greatest driver is us, the consumer, and our hunger for smarter, more personalized products delivered faster. This means one thing, and that is ever increasingly complex products. That's embedded software in virtually everything, from your watch to your toothbrush to your vehicle to your airplane seat. In fact, pretty much everything out there. Interdependency, connectivity, and scalability rely on efficient designs, visibility, and a single source of truth. The answer, of course, why we're here today, and that's MBSE, Model-Based Systems Engineering. It's a subject that we as XD Innovation committed to some time ago, and we are now helping various organizations with MBSE advice and expertise. Today, it's our second show on MBSE, the model of models. Let's do it. So MBSE, the model of models, what better way to dive into this than with our close friend and who is pretty much one of our very own, Alec Jackson. 8 years dedicated to MBSE cross-industry. He's been working with NASA for some time on advanced urban air mobility and Army hypersonics, never mind Ford and John Deere, to name but two more. We've agreed the world needs to be learning about and adopting MBSE, and it's our job to bring that message to the world. Let's get this going. Ready, set, go. Oh no.
What kind of plane is that?
Is that the new supersonic airplane everyone has been talking about?
That looks so complex. How did they actually design it, and in such a short amount of time? What kind of plane is that?
Is that the new supersonic airplane everyone has been talking about?
That looks so complex. How did they actually design it, and in such a short amount of time?
Okay, Alec, can you hear me loud and clear?
Yeah, now you're good.
Okay, good. I'm glad we have people back. Thank you, Ramon. Welcome back, Alec. How are you, man?
I'm doing fantastic. Just finished up a move this weekend, so a little sore, but we're alive.
Boxes everywhere. I got it. Good to have you back. You and I have agreed to do this monthly now. Keep nodding your head. Just make sure we're clear on that. And to demystify MBSE over the coming months, that's the plan. Before we jump into the model of models, aka MOM, as you like to call it, but not to be confused with manufacturing operations management. Audience, this is what we're going to be doing today. So we're going to take 5 sections, model of models, where it's coming from, Secondly, what's the foundations and principles? Then we're going to lean into how is it going to look in a logical and physical model. And lastly, finish up with how the model of models differs in MBSE. Please, everyone, as you think of a question, throw it into the chat. And at the end of each section, we're going to try and pull on those questions and have Alex answer those. And if not, we're going to leave some of those to the end as well. So let's get the world talking MBSE and let's get the show on the road. Alec, first up question. Many people are saying, yes, MBSE is good for aerospace and defense, and maybe even extending into discrete manufacturing, automotive. But how transferable is this into other industry verticals?
Yeah, so I've heard a lot of same statements similar to that. The thing is, right, it's a process. So if you can envision what you're working on as a system and truly leverage the process to optimize that system, it can stretch into any other vertical you're thinking of. I've seen in healthcare, I've used it in organizational system improvements. So, and with major return on investment.
Okay. Healthcare, are we talking kind of medical devices or into pharma?
Well, think about this, right? Your body's a system too. So yeah, I've seen it with like biotech, of course, right? It's a traditional system, but even like drug, pharmaceuticals and things of that nature, they're starting to go into modeling how those cells will actually break that stuff down and time of response and things of that nature.
Yep, got it. Okay, so for me, the top 3 reasons for MBSE correct me if I'm wrong, is 1, it tends to confront visualized complexity. It enables product agility and numerous unique personalized variables. Second, it enables reuse and inheritance. And lastly, arguably helps in managing multiple product lines. Is that a fair summary?
Yeah, and then with the last one, I mean, so realistically, you have to be careful where you put that, right? Because, if you go and log on to like Ford.com or another automotive website, they can guide you to, do you want to select red as your color or leather seats or whatever, right? That's more of the PLM, PLE kind of thing. But here, if you can get it into that architectural side, like what are the subsystems, what are the components, and how do they all work together, then yes, it's very efficient for that.
Okay, good. All right. So let's dive into the model of models. What is it? Why do we have it? What's the goal of it? Walk us through that, Alec.
Yeah, absolutely. So let me know when you guys can actually see my screen.
Got it.
Perfect.
Got it.
All right, so the model of models methodology is a MBSE methodology that's used for maximization of reuse, modularity, and traceability. So that means it's not without investment, right? And we're going to look at what this actually looks like. So the first thing that we're going to do is I'm going to start with the goal. So it's always good to bluff. So what we're trying to accomplish up front. Then we're going to look at the foundation upon which it's built, and then we're going to go through the method itself. So the goal, right? So what we're trying to accomplish. So let's assume that we're starting with a blank slate, right? So we don't have any systems and we don't have any infrastructure, and we're just going to begin from scratch. So let's say, of course, we get a really complex project for the first thing that we receive, right? So we're going to get this F-16 that's going to pop in, right? And so what we do in the model of models side is we define the taxonomies of the different systems down to the actual variant of the system that's being built. And what that means is we're actually spending time crafting what is the definition of an airplane, what is the differentiation of a combat aircraft from that standard template, and then going into the fighter side of things and inheriting those common attributes down as much as possible to reduce the amount of work when we're actually producing these things. In addition, so just so you're aware, we do that process with not just the prime systems being built, but even their subsystems, and it's a multidimensional methodology. So what we'll do is notice that we see radar library here, we see aircraft library here. They're both 2 separate projects because I could be using different radars in applications that are not aircraft. So we do the same process, so architect the taxonomy all the way down to the radar that we're actually going to be using. And then finally, same thing for something even like a weapon system, so missiles. So again, going down into the types that we're actually leveraging that are being used for this F-16V. Now, what you'll notice, right, so these arrows are telling you this is going in. So this is all investment at this point. And so you should be anticipating that your upfront investment, yes, is some, I wouldn't say high, but it's there, right? You're going to have to deal with it. But the value is that you're going to reap that investment from this point forward. So the next task, okay, go and do the same thing for the F-21. Well, the nice part is, at least when I built these slides, the idea was that they was using the same radar. I probably need to fact check that. It's been a while. But that said, at that time, they were using the same ANAPG, which means that if you've already architected it for the F-16, then just use it. There's no time to go and rebuild it. Same thing with the two missiles, right? For the AIM-120 and the AIM-9X, the Sidewinder and the AMRAAM, if you already have them architected, there's no reason for the rework to go and re-architect that. Pull it from the library, and now you have your time back. And what we've seen in certain programs is up to 80% return on investment by pulling from libraries. I mean, you're only spending, you know, less than a quarter of the time on the architectural development side.
Yeah.
Sure. And then the nice part is it's extensible, right? So then you get something like an F-35 comes around. In this case, well, we haven't built this. It's a new type of radar. So we're going to have to put a little bit of investment in this point. But notice that taxonomy is still there. So we don't have to redefine the taxonomy. We just have to go and put the actual details behind the radar itself. And then same with the missiles, since it's using the same missiles, we're not having to spend any time there. So you'll see still return on investment, even for things that might not be synonymous with the original artifact. If they have any commonalities, you get that reap every single time.
Great. Nice. Nicely explained. Good. I got one question that came in before the show that I'm just going to throw in here. Okay, we got it here, which is, I'm in the CPG food and beverage production sector. How can I use MBSE?
Yep, absolutely. So again, take that step back, like I mentioned at the intro, envision what you're doing as a system, right? And apply those systems engineering techniques using the model as a way to do it. Think of your production system in such a modular format, right? You probably have different manufacturing equipment or other systems that you're integrating together to get the final product. And so with that, look at their interfaces, look at the values on them, the time at which they process whatever, and feed them into one another, making sure that their interfaces connect, their functions are exactly what you're expecting, and their timing's aligned before ever designing and actually building that facility. And so you'll still get a reap on investment if you do it correctly.
Great. Good job. Thank you. Audience, please, questions, bring them on in. Whenever you feel they come to mind, throw them into the chat. Let us know. Let's move into section 2, Alex, which we're looking at explain the principles, what's the foundations of OOSM, and then start to look at the kind of concept models that you would be using.
Yeah, absolutely. So OOSM is the Object-Oriented Systems Engineering method. It's a very common methodology that's used in the field. Realistically, it's built on the principles of object-oriented systems engineering. Object-oriented software engineering. And what it does, just based off of that, is because it's that top-down taxonomy-driven design, it really helps with the reuse because you're defining high-level classes and reusing those attributes across for lower levels specializations like we saw in the library. Inheritance is how it's doing that. And then it's also enables the agility side because it's top down. So you're able to have that integrated network of functioning systems and subsystems. And if something must change, can automatically see the impact without having to do an advanced query to identify what's impacted by that modification. The concept model, so for OOSM, and then again, OOSM's just kind of like a guidebook. So this is a way to do OOSM. But typically what you're doing here is it's a high-level model, and it's projecting that business case for the system. So what we're looking at is the black box system that we're building. We're trying to take in our stakeholder needs, figure out what our use cases for the system are going to be, and what are those tangential systems that our system's going to have to connect to. which if you are thinking of it, this really is the optimal intersection for the work that the business analyst should be performing.
Okay. Just going back to OOSEM, what's the best description of an OOSEM process?
Yeah, absolutely. So like I said on that aircraft example, right? So you're going to start, let's say that we get a requirement that we need to establish air dominance, right? And we know that the enemy has advanced weaponry like missiles and things of that nature. So we already have enough up front to be able to go build out some lower level requirements attached to that, right? So first and foremost, air dominance. Ideally, that means that we're going to have some capability of flight in the system that we're going to be producing. So you're going to end up at something that's either a helicopter or an aircraft that can fly, right? You're going to accomplish that function. In addition, now that we have some intel on what the enemy is using, we should be deriving requirements from that. That's telling us, okay, we actually need to have something equal to or better than what they provide. So if they're using missiles, then we probably need them as well. And so what that means is we're able to flesh this out. So on the system level, that emergent behavior of flying must be there. And then we can go down and start to actually architect out those lower levels like a combat readiness system that will then identify incoming missiles and then enable us to fire our own and essentially piece that out based off of what we're seeing around us. I'm trying not to go into too many details because it can be very complex.
Yeah, I get that. What other kind of methodologies are out there that are standard in the market?
Yeah, of course. So I'll tell you that different tools advise different methodologies that help optimization of their tool. So for instance, there's another very popular MBSE tool in the market called Rhapsody. And so with Rhapsody, a very common methodology for it is RUP, which is the Rational Unified Process. And that enables it to essentially simulate and work like it's supposed to. So that's a very common process because it's a common tool. Another one's like Core. And so with that, it's also a tool driven. I will advise that for non-reusable models, Mike Vinarsic's hypermodeling methodology is actually extremely powerful. And so with that, if you have something that you're building that, let's say it's a one-off or it's an update or something along those lines that you're not going to necessarily need to retain a lot of rigor on the library side of things, I highly suggest looking into that.
Got it. Great. Back to concept model. Did I interrupted you? Did you cover concept model?
Absolutely. Yeah, I was done with that one.
Good. Let's just check in with the audience. We have a question here. How do you integrate different model types?
Yeah, exactly. So I'm going to interpret that as being different types of models, meaning data models, meaning an MBSE model to like a CAD model.
Yep.
And so with that, there are many middleware products that are currently on the market, like Intercax has Syndea, which is fantastic for data integration and even synchronization in some places, meaning I can define a structure in my MBSE and have the same structure in the CAD side of things. And in addition, there's another tool from, it's now ANSYS, who acquired Phoenix Model Center. And so Model Center allows you to do the same thing, but in the simulation side with established workflows, porting data across a sim.
Okay, good. No more questions from audience. Let's jump to part 3. What do we, let's talk through the logical model.
Excellent. So the logical model is the next step, right? So first and foremost, you should have a validation on your concept to ensure that your concept ideally should work, right? You should take this back to your stakeholders and say, hey, this is what I'm interpreting what you're asking for, and get their buy-in. Provided you have that, then go into the logical model. And what you're doing here, the goal is producing a template, a reusable template that can be used for all different all different variants of a classification of a system. So what we do is we start typically on the use case, what we defined before, and we actually lay out the mission scenarios. So we'll look at the functions that the different systems in a given use case are performing. We also will boil out functional requirements. So these could either come before this or after this. It's up to you. Some folks do requirements first, some do requirements after. Pick your poison. But you'll get your functional requirements off of this that are going to be established for all possible variants of this system. And then finally, you'll have your structure as well, where you're defining, again, that kind of template of this. In this case, it's an automobile, but classification of a system that highlights the subsystems and the components within those subsystems that will actually be true across all of the variants of this particular system.
Okay.
And the way that we do this, at least for our group, is we use a recursive mechanism to enable essentially improved navigability. So you're able to find the data. And what does that mean? Well, you'll see this thing that says logical, and at the level right below it is the automobile. And you'll notice at the same tier, you'll find the requirements, the functions, and the subsystems that all tie to this particular structure that's getting produced. Now, walking through the subsystems, the example being the powertrain, you'll find kind of a duplicate set of packages where the same kinds of data, but those that pertain to this subsystem live. So now, if I know I want to find that one requirement for the powertrain, well, I go and I find where the powertrain lives, and right beside it are the requirements for it, right? And you continue that process recursively until you reach what we call the component layer, which is the off-the-shelf layer. So when you're pulling stuff off the shelf and you're not necessarily detailing the inner workings of those COTS or GOTS products.
Okay. So just stepping back for a second, why do we, I think you probably answered it, but just to confirm, why do we need logical architecture in the first place?
Yeah, so I'm going to answer that with a quick story. So my start to this whole thing was when I was doing artificial intelligence on embedded systems, essentially right after college. One of the biggest issues that I found was the majority of my problems were not on the technical side, but were on the logical side of things. My logic wasn't correct, and that was manifesting itself in physical errors, right? And so what you need to do is have a logical foundation upon which the physical design is built to ensure that those problems are resolved. And for me, it was something along the lines of 80% of my problems. So one of my taglines I always say, pulling back the Alabama in me, right, is that essentially that physics don't fix bad logic. It never has. So if you're going to go and actually try to do physics, right, jump straight into CAD and build out some brand new spanking system with no knowledge of the logical inner workings of it, plan for rework. Because again, no matter how much physics you throw at it, the logic's not right, the system's not going to work.
Okay, so really the foundation stone of what's to follow. I got it.
Yep.
Just on the following slide, that taxonomy, was that kind of typical of logical elements that you look for across most?
It depends, right? I mean, typically, so for me, an electrical subsystem is usually unique to the systems you're building, right? You need to know what the draw is before you can produce the right subsystem to support it. Yeah. But infotainment and powertrain, those are specific subsystems that literally belong to automobiles.
Yeah.
So you might have an infotainment system on an aircraft. I'm not aware of it, perhaps. I don't do a lot of commercial aircraft, usually it's defense. But powertrain, that's automotive all day long. Okay. So industry specific generally. Okay, good. Let's break out to audience. Any questions in advance? How does MBSE typically impact a typical project in terms of deliverables, organizational structure, and processes? Yeah, so typically, first things first, realize MBSE is an investment. Your guys aren't going to wake up in the morning with Delegati's book and become competent MBSEs. You're going to have to get them formally trained. They're going to have time being led by somebody that actually knows what they're doing and coached in actually how to produce this, right? So that's the organizational structure. There is an investment period. From what I've seen, I've gotten programs off the ground in about a month, but that's a lot of full-time dedication. Usually it's between that sweet spot of like 3 to 6 months, and then you get some really competent folks running. Deliverables. So realistically, think about it this way, right? MBSE is systems engineering using modeling, right, to actually produce the artifacts. So your systems engineering deliverables should stay pretty similar. Now the format and the means to produce them might change because the model enables you like report generation capabilities and a lot of different tools, etc. But depending on what you're actually doing, your deliverables may stay the same. Processes, well, the one big thing to realize that a lot of folks forget is someone needs to manage this thing, not the data and the content in it, but the model itself, right? And so you need to have a baked in process of an architect that's actually ensuring there's no duplication, there's no conflicts on definitions, that interfaces mesh like they're supposed to, etc., to ensure that the data itself is maintained. And that's the biggest process increase that you're actually going to find.
You bet. Good. Great. Let's slide on into part 4, which is the physical architecture then.
Yeah, so the way that we do OSM is very logically focused, right? So we want the logic to be almost as perfect as possible, right? That's the big goal. Once you've gotten validation on the logic, then the physical can be as simple as going in here and essentially redefining your subsystems and components to select stuff that you put into your libraries, which we'll do later. So you're just redefining it and you're taking the off-the-shelf actual products. So like, you know, a Ford specific engine, right? Product number, etc., into the actual build to run trade studies on and find the optimal design, if you will, of this particular system. In addition, things like sensors and tangential things that aren't going to be common across all variants of a particular system will arise in this particular view as well.
Okay. What's the difference between a subsystem and a component?
Yeah, and so I'll tell you that this isn't an industry-wide definition. Different groups define different tiers of classifications when it comes to structures. What we use is the system is essentially the thing that you're building, right? So it's typically called a system of interest if you're looking through the NCOSE handbook. A subsystem to us is a system-specific aggregation of other working structures, be they other subsystems or what we call components, which are black box, essentially off-the-shelf component or structures that you're not necessarily putting a lot of definition behind. So that's the big thing. So subsystems belong to the system itself. So it's a specific thing, right? It's in that classification, where the component might be reusable across different systems and completely different industry verticals.
Got it. Okay. Let's spin out to the audience. Any questions that we've got? What kind of project metrics do you use, such as design quality, speed?
Yeah, so that's the fun part. So project management of MBSE is still catching up. And I've heard folks start to use the term like measure the number of diagrams produced or measure the number of interfaces on an element. Well, it's really easy to automate it. So I could produce 1,000 diagrams of different views of the data within essentially 2 seconds without building any content, right? Not an effective metric.
Yeah.
So typically what we're using are things a little bit deeper, and it does involve some actual thought, right? So the actual, like for instance, the number of requirements that have actually been traced to, or the number of components or functions that don't have a requirement, or the number of interfaces that have a successful connection, or the number of interfaces that don't have a connection, right? And so if you can group those together, you can start to see how much of your system has been fully architected. Good.
Very good. No other questions from the audience. Let's go to part 5, the model of where the model of model differs.
Yep, absolutely. So let's frame it for a second. So the problem, right? So typically in MBSE, we're getting into this big data issue where all information stored in this one giant model. And I've seen organizations, for instance, like Boeing and some others, not just a name drop, but they have really complex systems where they're keeping it all under one hood. And the issue you're finding is the same big data issue that others are finding, right? And so what that means is now these models are getting huge, in some cases, multi-million elements, which of course draws system resources and can lead to system slowdown. So there's, in cases, you'll hear horror stories of hours for commit, so 3 to 4 hours to actually commit a model to the server, or an hour and a half to open a model. Well, that's your productive business day right there, right? So that's unacceptable. And in addition, because of so many different cross-cutting domains all under one project hood, if you will, there's an issue with enforcement of tasking and responsibility and folks getting out of their swim lane and assisting others innocently with stuff that may or may not be true. And then finally, the management of these models becomes more difficult, right? Because there's more data. So they're now on the architect, they're trying to make sure there's no duplicates, no common spelling, that things are consistent throughout. Okay, now they're looking at across millions of elements to try to do that, and it becomes a major headache, right? Especially because guess what? Those models that they're doing that for aren't frozen. They're live models. So it's not, by the time they finally catch up, they're totally out of date by the time they restart, right? And so what ends up happening is because of these issues, we end up with a model that becomes a disaster. The term that you'll often hear is shelfware, right? Where it goes on the shelf, it's a nice to have, but no one's actually using it.
Yeah. I mean, is not virtually everyone going that whole megalithic approach?
A lot are, but you'll hear the term federated architecture. Now, I will tell you this. So megalithic is easier to manage in general in terms of a, let's say, authoritative kind of approach. Obviously, who owns it and categorizing it and tasking it, whatever. But one of the issues you'll find with that is what we see here, right? And so the converse is federated, but guess what? Federated, now you have to have extremely detailed management processes to ensure that integration occurs, the right data is revealed, that IP data is not revealed. And so it becomes more effort on the managerial side than the technical side. But if you can get it correct, it's a beautiful thing.
Yep. So it feels like the solution architects starting to take on project management roles. There's not enough project managers with experience of this necessarily. And that integration piece can be left out in the code, unfortunately, as well. So an evolving world, I guess.
Yeah.
Evolving world. Got it.
And as these things get more complex, guess what? The management of it's going to go up anyway. So you have to be thinking of that, right?
You bet. Good. I think we got one question coming in from the audience here. Let me just pick that out for the moment from Misael Gonzalez Santa Maria. What are the best or more useful findings you've got out of the validation and verification, right-hand side of the V methodology, process of the logic architecture development?
So doing the V and V on the logical side of things. So first and foremost, I'm a firm believer in a cyclic mini V approach. And if you're not familiar with that, it's a new kind of concept. It's think about agile almost, where you're essentially taking a slice of your logic and validating each tier to make sure it still makes sense. So that way you're not building things that are not correct, right? You don't go in a rabbit hole and then have to totally rework to fix everything. So tying back, I guess you said the question was, what is the value? Is that right? What's the value you're finding?
Process. What are the best or more useful findings you've got out of the validation and verification process?
Yeah. The other thing is, guess what? Communication, right? I will tell you that the biggest challenge that I have found in commercial industry, and it doesn't matter about MBSE or any type of engineering or heck, any type of business process, for whatever reason, while we're social animals, we really stink at talking to each other about things. And so doing that in a formal approach actually increases the likelihood that you're successful when you build the thing, right? Because typically you hear the term in their stovepipes, and even in mini stovepipes within their stovepipes, and aren't interfacing with each other and are making decisions that adversely impact one another and are not getting the checks and balances to actually fix those issues.
We're good. Hopefully, Marcel, that answers your question. Feel free to follow up if you have another. So moving on, is there a typical approach that you take to taxonomy?
Well, first, let's go just one quick step back to the facts. And so,
Okay.
so the problem, right, the megalithic issue that we were looking at,
Yeah.
the facts that we're finding that's leading to that is realistically systems today are so complex, are becoming system of systems. You have artificial intelligence, you have human factors, you have a lot of things that you didn't necessarily have to consider back in the day.
Mm-hmm.
In addition, there's very few individuals in a project that go from the system of systems level and stay with the project all the way down into the board layouts, like wrapping resistors and things of that nature. And what that means is typically there's a handoff, and at some point we accept a black box that represents the work someone else is going to do. And what we end up doing is running trade studies with said black boxes to actually craft our architectures. And what we end up doing, right, is guess what? If you strip back the wings of an aircraft, whatever, you will find boards and different components of all sorts of kinds. So it is this recursive process from that system of systems all the way through to the actual resistors, if you will, on the boards. Now that said, so back to the taxonomy question. So what we are doing, so there's a reason why I did that OOSIM, right? We use the same process, but the difference is, so this is the key difference. We have dedicated library projects that are reusable within our enterprise for whatever needs you have. And so what that means is, so going through that taxonomy, right? So from engine down into, so internal combustion engine, down into reciprocating, blah, 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 until you hit to the four-stroke. Four-stroke engines can be used in a wide variety of uses, not just automotive, but automotive happens to use them. So we will take that for our logical side of things, pop that into our automobile, and see how the four-stroke, with its functions and its values, impacts the logical design of an automobile. What we then do on the physical side, right, just like I showed before, is we have the corresponding physical components. These are the ones off the shelf. And we then take those and redefine that standard four-stroke engine with one of the more specific and run a trade study to see how does this architecture work with that specific engine being used, or whatever system, whatever component you want to insert there.
Yep. So I saw the logical and physical library models. What about from a conceptual perspective?
Absolutely. So, and this is on one of the slides we decided not to go with, so I kind of wish we brought it back. But that said, the conceptual side of things here is the system of systems. It's the usage of this specific system. So there's a language that I typically like to use for mission engineering. I'm a big fan. I've been using it for years, called UAF, or Unified Architecture Framework. It's fantastic for mission engineering, human factor modeling, etc., on the system of systems level. And so what ends up happening is these system architectures, so like the automobile, will feed up into there to see, for instance, how does a smart city run using a specific automobile?
Yep. Great. Good. Excellent. What do we got? We're going to sum it up, I think.
Yeah. So realistically, again, the premise of this, right, the big three were reuse, the digital thread, modularity. You'll notice I snuck in process as well. So again, for the reuse side, one of the biggest advantages to this MBSE thing is you're not having to re-architect. Once you build it, you can have it. It's a digital model, go reuse it. And it prevents having to pay for the same things over and over again. I mentioned the communication. So having a common process ensures consistency, and it improves the communication to ensure the right thing is being built at the right time. By doing this top-down approach, like we discussed, you've actually built that digital thread. So you have the ability to pull through the entire MBSE architecture and see where everything is interconnected. And the value being, you can now synchronize that into your CADs and whatever else and have that fully integrated digital toolchain. And then finally, the modularity. So now you can do that plug and play ability with these components and reuse them in different applications. For instance, the Navy, if you're not aware, uses jet engines to drive their ships, and they actually build a casing around it that does a lot of that work for them.
Yeah, that's great. Thank you, Alex. So what is the expected ROI from the model of models?
Yeah, so again, it's an investment heavy, so you're going to put time up front. But like I had mentioned before, right, I have seen some projects, again, it depends on what you've done in your past and what your future looks like. But I have seen some that had as much as 80% in the libraries where they only had to spend 20% of the forecasted effort on the architectural side. And so you get to decide, right? Do you cut the cost of your contract, or do you spend that 80% improving the engineering of other things and improving your overall system?
That's great. Good job. Thank you. It's a big one. The model of models. It's a big one, MBSE period. So if we have any other questions from the audience, please shoot them over. But I think we've covered everything there pretty well. Thanks, Alex, for that. Let's talk about next time around. Next time around, in about a month's time, we'll lock in that date. We're going to be pulling in one of the friend of yours and an MBSE expert direct from defense. Tell us about her.
Yeah, so you're going to be getting a good colleague of mine. Her name is Tamara Hambrick. She's a fun one, definitely. So watch out. She can be dicey sometimes. But anyways, no, she spent about 16 years with Northrop, and she has a wealth of experience on the MBSE side of things, especially in the defense sector.
Great. Good. Look forward to meeting you in about a month's time. Alec, again, thank you. You'll be co-hosting with me in about a month. So everyone, thanks for joining us. Much appreciated. Thanks for your questions. And we're going to see you in a month. Have a great month ahead and a great week. Thanks, everyone.
Thank you.